Okay, for this particular presentation, we're going to kind of extend our knowledge a little bit and move from the t-test to the type of statistical procedure known as an analysis of variance, or ANOVA. So to start this off, I have a little case study to start things off. Let's pretend for a minute that we're looking at the effects of a drug on memory in a very simple way. One group doesn't get the drug. They're given a group of words for 5 seconds and record how many words they recall. So subject 1, subject 2, and subject 3 words. The other group gets the drug and we record how many words they recall, and it's 5, 6, and 7. So as far as the type of statistic to do on that, I'm hoping you've already learned from previous presentations that you could do an independent sample t-test. Why would it be independent sample? Because everybody is only tested once, and we get their memory scores here. We have one independent variable, you might call that condition, drug condition, and we have 2 levels. One is no drug and the other is drug. So one independent variable, 2 levels, independent sample t-test you can do. If you look at the descriptive statistics there, you can see that for the group that got no drug, 3 people there, 3 people with the drug. The mean for one group is 2, the mean for the other group is 6. You know what that goes into, that the treatment effect would then be 4, so that's the numerator for the t-test, and then the standard deviation is 1. Can you figure out how they got that? Yep, well, the idea is if you have 3 consecutive scores for group 1, the sums of squares for a sample is always 2. The sums of squares is 2 there, and the variance would be 1, and the standard deviation is also 1. And that's the same for the other group, 5, 6, and 7. Any 3 consecutive numbers, the sums of squares is always 2, and the standard D is always 1. To go from standard deviation to the standard error, it's 1 over the square root of sample size. So 1 divided by the square root of 3, 0.57. So we got that in the upper chart. In the lower chart, hopefully you've recalled that the numerator for the t-test would be the mean difference, 4. The denominator, kind of related to the standard error, but it's called the standard error, the mean difference score, 0.81. When you put 4 over 0.81, it doesn't matter the sign there, the positive or negative 4. 4 over 0.81, you get a t-score of 4.899. And then the computer tells you, the SPSS, that the probability of getting that due to chance is 8 out of 1,000. That probability is so low that you basically decide that those results are not due to chance. Of course, you could be making a false alarm there if you said it is significant, and it is not, but hopefully we have a hit here. So you say it's statistically significant. You can hopefully write out the T statement here. T of 4 equals what? 4.899, comma, P equals 0.008. And then finally, the confidence interval we learned about, that for that you're not saying something is significant or not, or that the drug helped memory. But if you wanted to estimate how much, you are 95% confident that the drug helps out between, what, 1.7 and 6.3. The mean of that, the point estimate with a high degree of precision, would be 4, but you wouldn't have a lot of confidence in that. So that's the review from last time. If we move down to B, the approach we're going to talk about today, and I'll finish this part of the recording in just a minute or two, is called the analysis of variance. If you turn to your book, page 387 to 389, remember analysis of variance. Do you remember the formula for variance? That's sums of squares over degrees of freedom. So kind of related to that standard deviation, it was the idea of when you get the sums of squares, if you have too many people in one group and not enough in another, you need to divide by the degrees of freedom. So variance is a useful measure of dispersion, and we're going to learn a lot more about that in the computations in the next recording. Analysis of variance is a preferred approach to a t-test, because when you do a t-test, you have to have one independent variable and 2 levels. That's all you can do. But what if you have an experiment? Let's say you were doing a study and you had, let's say, 3 doses of a drug, or 3 different groups. Let's say you wanted to test a drug on young, middle-aged, and older people. That would be 1 independent variable, age, and 3 levels. You wouldn't want to do t-tests on those. With an ANOVA, you can have 1 independent variable and more than 2 levels. The other thing you can have is, let's say you wanted to look at the effects of how a drug maybe affects men versus women. So if you had 2 levels of drug and 2 levels of gender, then you have 2 independent variables, and that's another situation where a t-test, you really can't use a t-test there. T-test is only 1 IV and 2 levels. On ANOVA, you can have more than 2 levels of 1 IV. You can also have more than 1 independent variable. Thank you very much. Bye-bye.